Welcome back to our series on applied regression analysis. I'm Mark Ledbetter, and this is lecture video 20, and we are moving into chapter 6, correlation and its relationship to straight line regression. So in this chapter, we're going to define R, the correlation coefficient, talk about it as a measure of linear association. Then we're going to talk about R squared and how it measures the strength of the straight line relationship, what R squared doesn't measure. We're going to talk about how to do hypothesis tests and confidence intervals for R. Then we're going to test the equality of two correlations and talk about R squared in practice, and we'll have a supplementary lecture on the example. Okay, so last time we talked about chapter 5, and we were talking about the straight line regression and equation, and we were talking about the slope and the intercept and how to interpret those. We talked about the assumptions that we have to have for the straight line regression, and now we're going to talk about another way of measuring the association besides the slope, but it is related to the slope, as we'll find out. So the definition of R, first it's called the correlation coefficient, and it measures how two random variables are linearly associated to each other. And here's the lovely simple formula. No big deal at all. This is the definition of the formula. We would not want to use this as our calculation if we were going to do it by hand. In fact, in our introductory statistics class, we talk about a computational formula which looks like this. And then we have the square root of the sum, got to do n, sum of x squared minus the sum of x quantity squared, square root of n sum of y squared minus the sum of y quantity squared. So that's how we would do it by hand, and that's also how the computers do it. Now let's talk about a different way of defining this. We're going to call these the sum of squares. So SSXY is the sum of squares of x times y, and SSX and SSY are the sum of squares of y. And you can probably figure out what they're equal to. Here's SSX, here's SSY, and here's SSXY, the numerator. Okay. Now, in R, this is easily done with this formula here, that's in the box. So COR, and then you put your x variable, comma, y variable inside the parentheses. And it gives the correlation coefficient and nothing else. Okay, so we'll talk about how we can get a lot more and do a lot better than this function. But if you want to see what the correlation is, you can use this function in R easily again. So now, remember that our slope was given by this definition here. And again, this is not the formula you'd want to use to calculate it. Again, you'd use n sum of xy minus sum of x times the sum of y. And then this is this n sum of x squared minus sum of x quantity squared. Okay. You'll notice that the numerator of beta hat is the same as the numerator of R. It's the same formula. And then you'll notice that here we have the square of this term in R. So a lot of relationships. So we could rewrite this as SSXY over SSX. Now, if you remember that S of x squared is 1 over n minus 1 times SSX, or we could write this out the long way, x minus x bar squared over n minus 1. So that may be more familiar to you as the standard deviation. But we can also write y, as we've talked about, in the same form here. And now we have 1 over n minus 1 SSY, and that gives us this alternate equation for R, which is sometimes very handy. If we have the slope, beta 1 hat, and the standard deviations, then we can easily calculate R using this equation. It gives you exactly the same results. And I want to point out that we're going to report R to 3 decimal places. That's the standard. Now, the book does 2 decimal places for some reason. I'm not sure why, but no one does that. It's always 3 unless otherwise specified. It may be that because they're doing some bad rounding in their equations, they're rounding when they shouldn't be early, that to cover that up, they're doing 2 decimal places. So, if we look back at the age and systolic blood pressure data from Chapter 5, we can find that the correlation between age and systolic blood pressure was 0.658. Now, we could get that from the computer output that was there, and we just take the square root of the value of R squared that was printed out. And that's where I got this value, 0.658. Now, alternately, this is what was in the book, the example. They have the standard deviation of x, the standard deviation of y, and the slope, all rounded to 2 decimal places. So when they calculate this out, they were rounding to 2 decimal places. I rounded to 3. You see a little bit of a difference in the 3rd decimal place. Again, you've got rounding error, and that's what's contributing to this. But you just plug into our formula, and it's a lot easier to calculate. Okay, so let's talk about some properties of R. R is going to be between -1 and +1. So if you get a value that's outside of that, you've made a mistake. And no, it's not the formula. So that's the number one thing students say. This formula is wrong. I got a value that's outside of -1. But no, you can't. It's been looked at for over 100 years. I'm pretty sure we would have figured out if it could be outside of -1 to +1 by now. All right. Something to know is that R is dimensionless. That means there's no units. All the units cancel out. So you don't have to worry about making sure that things are in the right units to each other. They're not. R is independent of the units of x and y. If R is negative, then beta 1 is negative. If R is positive, beta 1 is positive. If it's 0, then beta 1 is 0. Okay, so basically they're the same sign. Now, let's talk about this as a measure of association. The more positive R is, the more positive the association. The more negative R is, the more negative the association. And if R is close to 0, there is little linear association between x and y. Remember that we could have some other shape, but some other association, and it could fool us into R and the straight line regression into thinking there's little or no association at all, but it may just be little linear association. Okay, and so by association we mean the lack of statistical independence between x and y. So if there's a correlation, they are not independent. Okay, there's some dependency there. So let's take a look at some different values of R. R is close to 1 here. Here, R is close to -1. What you were looking at is how close these points are to the line. And then R is close to 0. You'll see the slope is close to 0, but also the spread here. And then R is also close to 0. Here there's no linear association, but there's a nice parabolic association. But you see that the slope of the line is close to 0. R is close to 0. Now let's talk about the correlation population correlation coefficient. So we've been talking about the sample correlation, R. Now let's talk about the population correlation coefficient, rho. So this is rho, Greek letter, not P, but rho. And that's the population, not sample, the population correlation coefficient. And it's defined by this here. And x and y are the population standard deviations, and sigma xy is the covariance. Now, we have a formula for covariance, and if it's discrete, we have a formula, a calculation formula. We also have this formula that's the expected value of x minus mu times y minus, and that's mu x, y minus mu of y, the mean of y. So that's another way to write it for anyone who knows that notation. Okay, R is an estimate of rho. Any statistic, so R is a statistic, and rho is a population parameter. Okay, so let's take a look at some values of R. Here's R is 0.037, very close to 0. And we have the values here given here. So you take a look, and there's no line here, but if it's this close to 0, you're going to have a line with very little slope to it. And here R is 0.220, so that means that you can have a positive slope, but notice how spread out the data is from where the line would probably be. And now we have R is 0.342 here, and so we might have a line something like that, and we'll see a little less. Well, I think I may have drawn this one up here wrong. It's probably closer to something like this, and so you've got a lot of variation. And then this is R is 0.48, and so again, you're getting some variation, but not as much. And here part R is 0.814. And look at how, as far as distance from this line, they're a lot closer to this line, aren't they? Okay, so that's what happens as R increases. Now let's look at some quadrants here. If we, this point here would be X bar, and this would be Y bar. And so we divide this up into quadrants, and B and C are called the positive quadrants, and A and D are called the negative quadrants. And so if more of your points lie in the positive quadrants, you have a positive association. And if more lie in A and D, you'll have a negative association, and that makes sense, right? Because of the slope. Okay. So if the ith observation is in quadrant B, that's here, then X is greater than X bar, and Y is greater than Y bar, okay? And so this quantity is positive. And so this is the numerator. This is part of the numerator in the correlation coefficient. So, and the numerator is what's going to control the sign, because if we look back here at the formula, in the bottom we have squares and squares. So those are all positive, no matter what. Okay. Now, let's get back to where we were. Okay. If they're in quadrant C, again, now we have X is less than X bar and Y is less than Y bar, so these two quantities are both negative. Negative is positive. If we're in quadrant A, then X is less than X bar, but Y is greater than Y bar, so this will be negative, and this will be positive. Positive is negative. And likewise in D, we'll have X greater than X bar, Y less than Y bar, and so we have a positive negative, which again is going to give us a negative. So if we have more observations in the positive quadrants, R becomes larger, okay? All right, so that's enough for this video. Please don't forget to scan your lecture notes by midnight, the date listed in the course calendar. Be neat so you can read them, and they'll help you when you do your midterm, and they'll help you on your homework. Please make sure you update your formulas for the test and for the homework assignments. If you have any questions, come to virtual office hours. If you can't do that, then by all means email me, and we will see you next time.